What's up, my stats artists? Michael Princhek here, ready to talk to you about continuous random variables and how they tie into the normal distribution. Now, I don't want to go overboard here, but this might be one of the most important topics of all of AP statistics because it's going to really tie everything that we learned about probability and random variables in Unit 4 to everything that we're going to learn in Unit 5 over sampling distributions, which then bleeds into Unit 6 and Unit 7. So essentially, it's a really important video for you to learn about. Now, before we begin talking about continuous random variables, if you like my videos, you like learning from me, and you want more practice, please check out my ultimate review packet. The link is in the description below. I think it'll go a long way in providing you guys with study guides, practice problems, practice multiple choice problems, extra videos, extra formula sheets, all kind of fun stuff that I really think will help you. So please take the time to check it out. A lot of students are telling me that it's really what's driving them to getting really good grades in AP statistics and hopefully getting a great score on the AP exam in May. All right, let's dive into continuous random variables. All right, a continuous random variable is a variable that can take on any value within a specified domain. So it's a random variable because the outcomes are numerical values, but the numerical values that the random variable can take on are, well, essentially infinite, and every interval within the domain has a probability associated with it. The probability of an individual outcome of a continuous random variable cannot be calculated. We only look at the probability of intervals within the domain of the continuous random variable. Now, to better understand this, let's look at a couple of examples. First, let's look at the random variable b. It's the amount of time that it takes Gavin to brush his teeth in seconds. Now, if you think about it, that is, well, continuous, because when you got seconds, you can even give a decimal point, 11.3 seconds. You can even go 2 decimal points, 11.35 seconds. The whole point is that if I just look at an interval, even if Gavin just says, hey, listen, I know that it's going to take anywhere from 60 to 180 seconds for me to brush my teeth, any value in that interval is, well, possible, and the amount of outcomes in that interval is pretty infinite when you think about decimal places. Another example could be W, the weight of a great white shark in kilograms. Again, even if we look at a domain of, let's say, 400 kilograms to 1,500 kilograms, the weight of a shark could be anything in there, and it's really not even just whole numbers because, don't forget, you got those decimal places when you're talking about measurement of weight. So these are two examples of continuous random variable where the outcome is numerical value, but the list of outcomes is, well, pretty infinite, pretty long, pretty continuous. Now, with a continuous random variable, we cannot make a table showing the probability distributions. Well, we cannot make a table with infinite outcomes, so that should make sense. Remember, with discrete random variables, we can actually list each distinct outcome and the probability attached to each of those outcomes. But continuous random variables, unfortunately, we cannot do that because of the fact that there's infinite outcomes. So what can we do to show the distribution of a continuous random variable? Well, we could do so with something that's called a density curve. So we can't make a table, but what we can do is we could take a number line. And number lines are infinite, and you could zoom in on a number line for your specific domain. So let's go back to Gavin and his random variable b, how many seconds he brushes his teeth for. So here we have a number line anywhere from 0 to about 180 seconds, but just know that that number line to the right does continue to go on forever. Now, what we see here is a curve, and it's called a density curve. And the idea is where the curve is more dense, which is around 40 to 60 seconds, is where, well, it's more likely for him to take 40 to 60 seconds to brush his teeth. Now, we would describe this distribution as a little bit skewed to the right. And if you look at it, it basically tells us that the majority of the time, it takes anywhere from 20 to 80 seconds. 20 to 80 seconds has a lot of density to it, right? There's a lot of area in between 20 to 80 seconds. And then as we get higher and higher and higher, it becomes lower and lower and lower. And that's signifying that it's just less likely. There's less of amount of time where we see Gavin would brush his teeth over 100 seconds, 120 seconds, and so forth. So the idea is this. Under this density curve is an area of 1, or 100%. So of all the times it has ever taken Gavin to brush his teeth, all of them, 100% of those times, are under this curve. So we see that Gavin typically brushes his teeth maybe around 40 to 50 seconds. That's what's very common. But sometimes he takes longer, but The longer it goes, the less likely those times are. And sometimes C does brush his teeth really, really quickly, closer to 0, but again, that's also less likely. So the idea is the density curve allows us to see where the curve is more dense, which is where we see more outcomes. So the number line shows us the possible values for the continuous random variable, and the curve shows us, well, what's more likely and what's less likely. So now we could use this curve to talk about probability. So for example, we can maybe ask the question, what's the probability it takes Gavin 80 seconds to brush his teeth? Well, hold on, stop, time out. Remember what we said. Unfortunately, with the continuous random variable, we cannot calculate a specific outcome. So a specific outcome like exactly 80 seconds with a continuous random variable, unfortunately, we cannot calculate. But what we can calculate is an interval of outcomes. So if we said, what is the probability that it takes Gavin between 60 and 80 seconds to brush his teeth, we can answer that question. So what we do is we look at 60 to 80 on our number line and we shade in the area between. Now remember, underneath that entire curve is 100% of the times it takes Gavin to brush his teeth. So what we're looking for in that blue area, or purple area, whatever you want to call it, is what proportion does that represent? 20% maybe? I mean, it's definitely not really low, like 5%. It's also not super high, like 98%. So again, this is what we kind of have to do, is we just kind of have to estimate, okay, that area of the curve is what we're looking for, 60 to 80 seconds to brush his teeth, and that area is maybe roughly 20%. So 20% of the time, it takes Gavin 60 to 80 seconds to brush his teeth. So this is how a density curve can display the outcomes for our continuous random variable, and the curve, height, density could show us about the probabilities. Now here is our second example where we're looking at W, the weight of a great white shark. And here we see a density curve that's maybe more bimodal. We see two humps. We see a lot of sharks weigh around 650 kilograms. We also see another big chunk of sharks that weigh around 1,000 kilograms. In between, around 800, it's lower, which means less sharks weigh around 800 kilograms. And then we also see that to the far right, it gets less and less and less. So it would be very unlikely for a shark to weigh over 1,200 kilograms. And it would be the same thing on the other side. It'd be weird for a shark to weigh under 400 kilograms. It doesn't mean that there's no sharks down there. There's just less of them. Now, what could explain the bimodal nature of this? Well, if you know anything about great white sharks, you got females and you got males. So if we put them all into the same distribution, we're going to see a hump where the females are. And if you're not learning this for the first time, this is pretty cool, but female great white sharks are actually larger. So that would be the bigger hump centered around 1,000 kilograms, and the lower hump would be the male great white sharks that are centered around 650 kilograms. Now, don't forget, we cannot ask a question like, what's the probability that a great white shark weighs 675 kilograms? Can't ask that question. But we can look at an interval. For example, we could say, what's the probability that a great white shark weighs less than 500 kilograms? So what we're going to do is we're just going to put a mark at that 500 kilograms. We're going to shade everything to the left of it. And we're looking at what proportion, what percentage of the curve is represented by that purple area or pink area, whatever you want to call it. So again, 100% of sharks or 100% of weights of sharks are underneath the curve. That particular area would maybe be, I don't know, 4%, 5%. Again, we just kind of have to eyeball it and come up with the best answer that we can. But it's understanding that the area in that shaded region represents the probability of the proportion that we're looking for. Now, density curves come in all shapes and sizes, but there just so happens to be one density curve, one distribution that many continuous random variables fit. Now, maybe not perfectly, but approximately, and that model is the normal distribution. Now, a continuous random variable with a normal distribution is commonly used to describe populations. The distribution of a normal random variable can be described by normal or bell-shaped curve. It would kind of look like this. This is a very famous density curve. Why is it so famous? Well, a whole lot of those continuous random variables will fit into a density curve that looks like this. Now, in a density curve that looks like this, we see the majority of the data is in the middle near the mean. When you're nice and symmetric like this, remember the mean is going to be smack dab in the middle. And as we go to the far left or to the far right, we see less density, so less and less of the data. So the further values get from the mean, the less likely they are to occur. Values really, really low are super unlikely values. Values really, really, really high are also super unlikely values. Now, a curve like this normal curve, again, I can't emphasize that it really does fit lots and lots of types of data. So for example, the height of males in inches is a distribution that is definitely modeled with a normal distribution. So right smack dab in the middle, we see the mean of 70 inches. If you go ahead and Google the mean height of men, you're going to get somewhere around 70 inches. That's going to be right smack dab in the middle, and that is where most men fit. But 50% of men are taller than that on the right-hand side, and 50% of men are smaller than that on the left-hand side. But we also see that if we go up, 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 we eventually get to around 79 inches where, are there men that are taller than 79 inches in this world? Absolutely, but very, very few of them, a very, very small proportion. That section of the graph is not very dense. And the same thing when we go down the left, we see 61. There are just not very many adult men that are below 61 inches. Now, does that mean there's none down there? No, there's definitely some down there, but again, a very low proportion, which means it'd be a very low probability for a man to be down there. Why? Well, most men are closer to 70 in the middle. And again, this is exactly what a normal distribution is describing, where we see the majority of our data, the majority of our outcomes, the continuous random variable in the middle, and less to the left and less to the right, nice and symmetric. Now, please note that no continuous random variable is going to fit this model perfectly, but sometimes they will approximately fit this model. Now, since so many continuous random variables follow the normal distribution, at least approximately, we can create one model called the standard normal distribution that we could use to represent all of them. And we could build that model based on z-scores. So we should probably quickly review what a z-score is. A z-score measures how many standard deviations a particular outcome is from the mean. And to determine a z-score, we only need two really simple numbers. We need the mean of the population and the standard deviation of the population. And if you've learned anything about continuous random variables or anything about just random variables in general, we know that finding the mean and finding the standard deviation are two really, really important values. So a z-score formula is very simple to find a z-score. We simply take the individual outcome x that you're looking for, we subtract the mean, and we divide by the standard deviation. Make sure you do that in two steps. Subtract the mean first, then divide that difference by the standard deviation. And what you get is how many standard deviations a value is from the mean. Now, from that, we could build what's called the standard normal model, which is based on z-scores. So right smack dab in the middle, we see 0. Why? Well, because 0 is 0 standard deviations from the mean. The mean is 0 from itself. So right smack dab in the middle of a nice symmetric distribution, we see the mean. Then we could go up 1, 2, 3 standard deviations, down 1, down 2, down 3. Now, why do we stop at -3 and +3? Why don't we go further and further? Because when you fit a normal distribution, it is very unlikely for a value to be more than 3 standard deviations. Not impossible, just very unlikely. Same thing with -3. It's very unlikely for a data value to be more than 3 standard deviations below the mean. Could there be data down there? Absolutely, but it's just very, very unlikely. It's very, very less dense. There's not going to be much data down there at all. But this is a standard normal distribution based on z-scores. 0, 1, 2, 3, 0, -1, -2, -3, standard deviations from the mean. And as long as you follow the normal distribution, you could be put onto this standard normal model. All we need is your mean and your standard deviation, and we could get your z-score and find out where you fit on this model. For example, if you are a male who happens to be 75 inches tall, well, the mean's 70, so you're clearly going to be on the right side, but we can figure out exactly where you fit on the standard normal model by finding your z-score. So we're going to take that man who is 75 inches tall, subtract the mean of 70, divide by the standard deviation of 3, and we get a z-score of 1.67. So the red arrow indicates exactly where this man falls on the standard normal curve. But we can also look at sharks. Let's just say we have a male shark that weighs 715 kilograms. Well, if we find that shark's z-score, we're going to subtract the mean of 650 kilograms, divide by the standard deviation of 39 kilograms, and we get 1.67. So what we just discovered was that a man who is 70 inches tall and a great white male shark that weighs 715 kilograms, well, they actually have the same z-score. So they could be put onto the exact same spot of the exact same standard normal model, as long as both of their distributions follow a normal model, of course. Now, then we could ask ourselves those probability questions. What is the probability that a man is more than 75 inches tall, But based on our model, that would be the exact same answer as the probability of a shark weighing more than 750 kilograms. Because they have the same z-score, that means they fall at the exact same spot on our standard normal density curve, and that's having a z-score greater than 1.67. So again, a male being greater than 75 inches, a shark being greater than 750 kilograms is all the same as a z-score being greater than 1.67. So we're looking at that purplish area and we're saying, all right, what is that probability? What is that proportion? What is that area? And I'm going to be honest, it looks pretty low, maybe 4 to 5%. It's only a small fraction of the entire area, and we know that underneath that entire curve is 100%. The problem is that we want to be able to find that area exactly. We don't want to just guess, 4 to 5%. That's not very accurate. Well, because we follow a normal distribution and they both fall on this standard normal curve, guess what? We actually have a way to calculate that probability pretty exactly. Now, it turns out that mathematicians have created a function or a formula that can find probabilities within a standard normal model. Now, it may sound like a ton of fun to use super high level calculus to actually create that function, but listen, that's not what this class is about. We're just going to use the function. We're not going to do all the high level math. We're just going to use the function that's going to tell us what that area is. And all we need is the z-score. Now, the function command on the calculator that's going to do all this for us is called normal CDF. To access it, you hit the second vars. That vars button stands for variables. And this screen is going to come up. We see two commands here, normal PDF and normal CDF. We are not going to be using normal PDF in this course. We're going to be using normal CDF. So here's how normal CDF works. The command will find the probability of a continuous random variable being in between two z-scores. So when you're in normal CDF, you're going to type in a lower z-score and a upper z-score. And what normal CDF is going to do for you, it's going to calculate the probability that a continuous random variable falls in between those two z-scores. Now, since we want to use that standard normal model, we want to leave the mean as 0 and we want to leave the standard deviation as 1, because remember, that's what the standard normal distribution is built on. So for example, if we're looking at a standard normal model and we have a z-score of negative 0.5 and we have a z-score of 1.8, and we want to find the probability or the proportion or the area in between those two z-scores. So first we see that that's a pretty dense, big area. Now, how are we actually going to get this answer? Well, it's really simple. We're going to get second vars, select normal CDF. The lower value is going to be negative 0.5. The upper value is going to be 1.8. And we're going to go ahead and hit enter, and it gives us 0.656. That means that the area in between those two z-scores from the standard normal model is 65.6%. Of the entire area, which is of course 100%. That means that the probability that a z-score falls within that range is 65.6%, or the proportion of all z-scores that are in the standard normal table that fall into that interval is 65.6%. You get the idea. So let's actually go back to our problem dealing with male heights and male shark weights. Now remember, we found out that a 75-inch tall man and a 750 kilogram shark have the exact same z-score, and we're trying to find the probability that a shark or a man is more than 75 inches or a shark more than 715 grams, but both of those are equivalent on the standard normal model to a z-score being greater than 1.67. All right, so how are we going to do this on our calculator? Well, we're going to go ahead and grab normal CDF. We're going to type in a lower value of 1.67. Now, here's the problem. There is no upper value. We technically want to go towards infinity. I know on the model it stops at 3, but remember it technically goes well past 3. It's just very less likely well past 3. So we don't have an infinity button on our calculator to go greater than 1.67. So we're just going to use a really big z-score like 99. I mean, 99 z-score would be amazingly large. But essentially, we're just using 99 to act as an infinity. So we want to find the area on the standard normal model, starting at a lower value of 1.67, going to an upper value of 99, essentially infinity, and hit enter, and we're going to get 4.75%. So 4.75% of men are taller than 75 inches. 4.75% of male sharks weigh more than 715 kilograms because on the standard normal model, they both have the exact same z-score. Well, remember earlier, I guessed around 4 to 5%, and I was actually really close with that estimate. So that's how easy it is to find probabilities or proportions or area within a standard normal model. Now, again, there's only a couple rules. Rule number one, you have to follow a normal distribution. If your population does not follow a normal distribution, unfortunately, you cannot use normal CDF because normal CDF is based on it using a normal distribution. And the second thing you need is z-scores. When you type in that upper and lower value, you have to type in z-scores. So you do have to work to take your continuous random variable, subtract the mean, divide by the standard deviation to convert it to a z-score. Let's look at a couple more examples of exactly how this works. Another continuous random variable is the weight of a leatherback sea turtle. How much does a leatherback sea turtle weigh? Well, it's a numerical value, and with decimals, it's going to be a pretty infinite list. Now, we do know that the mean is 880 pounds and the standard deviation is 73 pounds. And we know, most importantly, that the distribution of this continuous random variable approximately follows a normal distribution. That allows us to calculate probabilities within it. So here are three questions. What is the probability that a random leatherback sea turtle has a weight less than 800 pounds? All right, so the first thing we need is its z-score so we could put that turtle on the standard normal model. All right, so we're going to take 800 minus 880 divided by the standard deviation of 73, and we're going to get a z-score of negative 1.10. Now what we're going to do is we're going to go and grab normal CDF so we can find the area below or to the left of that z-score, because again, we want to look less than. All right, now technically the lower value is going to be negative infinity, way to the left. Well, we don't have an infinity button on our calculator, so again, our lower value is going to be negative 99, and then the upper value to the right would be that negative 1.10. That's going to represent the area from negative infinity to negative 1.10. Go ahead and hit enter, and we get a probability or a proportion of 13.6%. So there's a 13.6% chance that a random leatherback sea turtle would weigh below 800 pounds. Or the proportion of all leatherback sea turtles that are less than 800 pounds is 13.6%. All right, another question could be, what is the probability that a random leatherback sea turtle is going to weigh somewhere between 800 and 900 pounds? Well, once again, the first thing we got to do is get the z-scores for both 800 and 900. Well, we already know the z-score for 800 is negative 1.10. Now we got to find the z-score for 900 by subtracting 880 divided by the standard deviation of 73. And we get a z-score of positive 0.27. So now we're going to go to that normal CDF. We're going to select the lower value, or the number to the left is that negative 1.10 representing the 800. And then to the right, the upper value is the 0.27 representing that 900. And hit enter, and we get an area of 0.471, or the probability of getting a leatherback sea turtle between 800 and 900 pounds at random is 47.1%. One more question here is, what is the probability that a leatherback sea turtle is greater than 900 pounds? Well, we already have the z-score for 900 pounds to be 0.27. So we just got to find the area to the right of 0.27. So we're going to go to our calculator, grab normal CDF. The lower value is going to be 0.27. That's the value on the left. And we want to go all the way to the right. We don't want to just stop at 3. We want to go towards infinity. So we're going to put in a 99 as that upper value, a really big z-score. And we get a probability of 39.4%. So it's a 39.4% chance that a random leatherback sea turtle is going to weigh over 900 pounds. And that's it. That's really how easy it is to find probabilities for a continuous random variable if it follows a normal distribution. All you have to be given are 3 pieces of information. First, the mean. Second, the standard deviation. And third, you have to be told that the distribution of the continuous random variable approximately follows a normal distribution. Now, if you don't approximately follow normal distribution, then unfortunately, we can't calculate probabilities. So if you go back to the amount of time it takes Gavin to brush his teeth, or the weights of all great white sharks, males and females, we saw that bimodal model. Unfortunately, to find probabilities in those distributions, we just have to kind of eyeball it by looking at the picture. We don't have any command on our calculator that is going to be able to do it for us. This is because the normal distribution is so famous and so often used that, again, mathematicians created functions and formulas that could do it for us. Now, I've been teaching you in this video how to do all of this using your TI-84 calculator. Now, you can also use what are called z-tables, where you actually look up the z-scores and you find the probabilities. I'm not going to show you how to do that in this video, but maybe your teacher is teaching you how to do that as well. There's also plenty of websites that work just like normal CDF. You type in a lower, you type in an upper, and it gives you the probability or the proportion. Some of those websites even draw you a nice little picture of the normal distribution they shade in that particular area. But the problem is, on the AP exam, you are allowed to use a TI-84 calculator. So that's why I want to show you how easy it is to find these probabilities using a TI-84 calculator so you can use it on the AP exam in May. All right, that's it for this video over continuous random variables and finding probabilities if they follow a normal distribution. This is part one. There is going to be a second video where we do even more with this scenario of working with the continuous random variable and using the normal distribution. There's actually a lot of really cool problems you could do. Yes, they might be challenging, but to me, challenging problems are cool. So please stay tuned for part two. We're going to do even more with this scenario. All right, hopefully you enjoyed this video and hopefully you valued it, because it really is an important tool to be able to use the normal distribution to find probabilities.